I'll begin my session now. So welcome to the course Calculus of One Variable. So over here we're going to understand how the function changes when you change the input. We want to understand the rate of changes. We want to understand how we record all those changes. And why is this important? Because whenever we have something which doesn't behave linearly, you know how to study systems when you have a linear variations, because those things you have studied in your school and high school. But we are very much interested in case when we have a non-linear variation and we want to understand how things change. We want to understand the evolution of the system, maybe anything, maybe system, maybe portfolio related thing. For example, we talk about various terms like rate of change, we talk about velocities, we talk about various concepts like distance, time in physics, for example, and we want to just play with those quantities and want to understand how we can describe a system. So this course is all about uh, to give you the fundamental aspects of calculus, that too of one single variable. Basically, we want to understand what happens when you give a input, a single input, and want to understand a single output kind of a relationship. And this basically is a fundamental tool for the students who are studying science, engineering, and economics. In economics, we also use this particular thing called as calculus, because over there we want to understand how the elasticity of demand things happen. We have those demand and supply kind of relationship and want to understand how demand affects the supply and how supply affects the demand. So I hope everyone can hear me. Like, just can anyone give me thumbs up or something like that before I formally begin? Any thumbs up? Anything that I'm audible? Yeah. Okay. Thank you. Okay. So currently, so let me first introduce myself. So my name is Bhavesh Gupta, and I'm currently doing PhD from physics department from IIT Madras. So here's my Gmail address where you can mail me for any questions. Like for example, if you have any doubt related to any concept, so you can mail me on this email address and can ask question. Maybe you can ask how can you understand this particular concept, because there are many confusing things you will find in this particular age, because the concept of calculus is not that very simple. When you go more deeper and deeper, you will find many more intriguing questions. So I guess this is a fundamental course, so I hope you're not dealing with very difficult questions in this course. So normally this course is designed for the first year students who are basically trying to understand the behavior of the system, and in particularly the mathematics students. And the prerequisite of this course is to you need to know what are the basic mathematics that you have learned in your school, and little bit of idea what do you mean by numbers, what do you mean by fraction, how to do the simple algebraic calculations. For instance, the most important idea is called the variables. What do you mean by variable? Hope these ideas are all clear. Even if you have any doubt, just let me know, or just comment in the chat box like, hey, I have a question in this, I don't understand, what do you mean by this variable or something like that. Just let me know. And hopefully you understand what all things we have covered so far in week 1. In week 1 there were 5 lectures, each per day. The first lecture was based on numbers, where we talk about various kinds of numbers. For example, real number, integer, rational numbers, irrational numbers, and how they are related to each other. Are they relation or not? Are they a bigger part of a subset or something like that? So various things we have studied in the first lectures related to the numbers. But in the lecture 2 you have seen the concept of countability and countability. So the idea of countability is very important, because in mathematics we want to index everything, because indexing helps us to do programming as well. When we trying to do certain programming in mathematics or physics or anything, we have to do something called as indexing and all. So so whatever things I'm currently telling you now is just giving you the background why we are interested in learning calculus. This has nothing to do with the course. These are the future applications of the calculus. So now let me begin with the idea first. I hope in the lecture when you saw these numbers, right, where the professor talked about set theory, the abstraction of counting, and what do you mean by numbers. For example, this integer, natural set, okay, and the idea of divisibility, prime factors, how do we write prime factors, and we also saw the idea of mathematical induction, okay, and how can we prove certain statements, certain mathematical statements using this mathematical induction. For example, in the lecture he used this mathematical induction tool to understand whether this mathematical statement is right or wrong. Yes, I'm recording this session, yes, and this session will get uploaded in the YouTube. I will send you the links, so in future also you can go and just see what all things I have discussed so far. You can open your mic and can share me the questions you have, because the whole idea of doing this live session is to understand what questions do you have in your head, the questions you have in your mind and you want to ask. Okay, so this is the whole idea of that, this session. So it's just not me talking alone, right? So I want the session to be bilateral thing. I want you guys to speak up, so that accordingly I'll tell you what the concept is and what are not. So I want input from yours, because that's how the lectures will go. Because I'm not here to teach concepts, right? Because I have already done lectures, right, related to this. So I don't want to repeat things. I mean to say, I just want to clear your doubts. If you, I have some questions to discuss. So please let me know. Does anyone have any question related to the first lecture related to the numbers? Please open up your mic and just switch on your mic and just ask me. We did various kind of numbers like natural numbers, integers, rational numbers, and we also see the first example of irrational numbers was given through this Pythagoras theorem. Using this Pythagoras, we constructed this root 2, which is not done algebraically, right? Because we know the irrational numbers cannot be written as a p by q form. It cannot be written as a fraction. So the construction of irrational number is always geometrical thing. For example, one of the famous, my personal favorite irrational number is number pi, which is an irrational number, and the construction of this pi is such that the construction of this pi is done when you have a circle, right? And in circle we always have this diameter thing, right? And we have the circumference. So this pi is basically ratio of circumference over diameter of a circle. So all the irrational numbers have the geometrical origin. They are not origin by the algebra. Okay? So this is the important thing I want to emphasize in the currently. In this session, in the lectures, you might also seen something called as format numbers. Format numbers are basically the representation how we represent a number. So every number can be represented in this way, especially prime numbers. We used to define prime numbers in such way because this form is very useful. And using this form, we can prove whether this number is prime or not. So if we are able to have this form, then we can say, yeah, that's a prime number. Does anyone have any questions so far related to numbers? So that I can jump to the important part. Okay, let me start with an important thing. So the lectures the professor have defined something called as a function. And the first thing I need to be very clear that function is basically, it's a kind of a black box thing. Okay, and why we are interested in this black box? Because this black box is an agent which does a work for you. Okay, so what you do, you provide some input to this black box. I don't know what it does, but it does something, and in return it gives you some y. And if you know the structure of this black box, you can manipulate. You can do manipulations such that you control this y based on your inputs. And one more important thing is that we sometimes write this as y equal to fx, and we call this an equation, and this equation basically tells you the structure of the black box. Structure of this black box. And why am I calling it a black box? Because I currently don't know, but the moment I give you the structure, the whole idea will be clear. For example, if I have structures like x square, so basically what this black box does is basically what it does, this black box, let's say you gave an input x, so it gives your output x square. It squares. This is what a function does. And let's say if you have a function, for example e to the power x, so what this function does, it exponentiates with a number e, and number e is a irrational number. Okay, and such that your output is always positive, right? Because exponential of any number is always a positive number. So from this example we can see when to use which structure. For example, if I ask you what is the square of a number, so I would prefer to use this structure. Okay, and let's say if I give you some random numbers, it can be positive, negative or anything, but you want only the positive things, so you can exponentiate that number in order to get a positive number. No matter what input you give, you will always end up as a positive number. So you need to describe and understand the system, and based on that understanding you can have a structure of that function and you can play with that. For example, when you have a function, let's say written as this way, fx equal to sin x, so this is a trigonometric function that you have studied in your class 10th and also in the higher schools. So what this trigonometric function does, it basically explains you the oscillatory behavior of a system. Okay. For example, you have a pendulum, right? A pendulum kind of thing, and you want to understand the motion of this pendulum. So what we found that the displacement of this pendulum, the kind of motion this pendulum does is an oscillatory, is a some kind of an oscillation happening, and we mathematically write these oscillations using this sine function. And if you see the graph of the sine function, looks like this. So this is your sine function, and this is your input. So what we see here is that based on the functions you can mathematically describe a system or anything. So the next question comes is, why do we need the idea of function? Because my main topic is to understand limits, right? Because what happens when you have a certain behavior in a system and you want to understand what happens exactly in that situation, and you don't know, because somehow you are unable to do experiment, somehow you are unable to probe the system in that particular situation. Let me give you an example. For example, let's say you are trying to do a pendulum experiment, okay? You're trying to do a pendulum experiment, but what happens? And you're trying to get a plot, for example, time period versus this distance displacement you did, right? And I just want to understand, if I increase my amplitude of this pendulum, I just want to understand the behavior of the time period, and I found my expression to be as this, some kind of this. But I'm asking you a question, what happens over here? I'm unable to claim any answer because maybe experimentally I cannot get this right. I might be very close to zero, but not exactly zero. So the question comes, what happens when you are very close to zero? Like maybe experimentally you couldn't do. Maybe you don't have that good amount of good experiment. Maybe your computers are not good enough. So that's why we need the concept of limits. So the concept of limits tells you the behavior to a particular situation, to a particular scenario where you are unable to find. Maybe experimentally, maybe through some doing some computer thing, we were unable to find. Now you want to estimate. So what basically limits gives you? Limits gives us an estimate. It just estimates. Uh, for example, let's say I have a function. For example, like this way. Yeah, it was going in a smooth fashion, and somehow I'm unable to do experiment for this particular values. Somehow I'm unable to do the experiment. Let's say my computer shut off. I don't know what happened to this computer. Then I had data for this. So can you estimate here what happened? And we want that estimation because I might be doing some experiment which is very important for human mankind. I just want to understand, can I estimate this? And this estimation is very important when it comes to market, when you do stock market and related thing, finances, economics, where you just want to estimate future, which haven't happened, but you want to know what could happen if this is the trend, is what going on. Okay, so this limits will help you. So what do? You approach to this particular zone two ways, as what professor said. The two ways you can approach. The first way you can approach is from left hand side. Okay, another way you can approach is from right hand side, and you go as close as possible to this unpredictable to this unknown situation, right? And as you move along, you come across this particular point, this, and you study the behavior at these points. And if we found the behavior of the study at these 2 points is same, then we conclude the behavior is also same, which we don't have the idea. For example, over here, let me do it little properly. So let me give a good example. Let's say we have this example. Let's say x y equal to fx. Something happening there, and let's say I don't know what happened to this point. I don't know. Just want to estimate. And I know what happens to the other points, but I didn't know what happened exactly at this point. Yes, ask. You can unmute yourself and ask. Anyone have a doubt? So idea over here is to basically understand what happened here. Is the value is something else, or is this value which we could understand from this particular trend. So what limits basically tells you, it helps you to estimate what happened at x equal to 0. So basically limits gives answer what happened at f of a. It just tells you what happened at this point. And how do we study that? We basically come from the left hand side, go as close as possible to this x equal to a point over here. We go as close as possible, but we are not exactly going to x equal to a, because if I could go exactly equal x equal to a, then that's not a problem, right? I just have to do the experiment and understand, yeah, this happened. But the problem is I'm trying to do something in which I cannot go to x equal to a, and I just want to understand what is the behavior at x equal to a. So what I do, I try to go as close as possible to x equal to a from the left hand side. Okay, and we just try to understand what is the value that I have achieved, and we represent that value as a minus, and we call this as left hand limit. And again I try to approach from the right hand side, as close as possible, and again do my measurement or anything, whatever the thing which you like to do, and I represent that as right hand limit. So if I found that these two limits are same, and if I found that left hand limit is equal to the right hand limit, then I conclude that my actual answer is both left hand limit and right hand limit. Anyways, because they are same, so we can choose anyone. So the idea is that if you are trying to understand the behavior of a system or anything, if you are trying to understand behavior at particular point which you cannot get access to it, so what you do, you try to understand the behavior in the vicinity of that point. Okay, we try to understand the behavior to the vicinity to this point, and just try to understand what is the behavior around the vicinity, and from that analysis you can claim what happened to exactly at that point. So the idea is that, let's say this is something we want to study, right? And let's say there is a puncture in this particular sheet, the sheet of paper, there is some puncture, and you just want to understand what was here. I don't know what happened, like there was some puncture now. Earlier there was not a puncture, but now there is a puncture in this particular sheet, and just want to understand what was here. So what I do, I study in the vicinity of that puncture. I study in the vicinity, close vicinity, very close to that point, and from the behavior of the vicinity I can claim what has happened to that puncture area, to that puncture site. I can claim. But the idea is that the behavior of this orange color which you see must be same somewhere. If I see the behavior over here something else, and if I see behavior over here something else, and let's say over here something else, then I cannot say in the puncture area there was a different color. I cannot say, right? So what's my belief is that in order to say something concrete, answer, I'll study in the vicinity where I want to understand, which I couldn't understand because of certain reasons, some experimental problems. So based on the understanding of the behavior on the vicinity points, I can claim what happened. I hope my idea is clear, right? Any thumbs up so that I can understand why do we need to understand limits? Why do we need to understand function? Because these are the mathematical descriptions of a real life problem. Because functions can be seen as some agent which does work for you. And for example, I don't know what is the square of a number. So what I do, I give this number to the function, Yes. How do we find the answer at x equal to a by using the vicinity points? Yes. So the idea is that the same thing. The idea is that if the behavior around that point is same throughout, then we say that the behavior at that exact point is also same to what we have found in the vicinity. But if around the vicinity the behavior is different, then I cannot say, then I cannot give answer to that exact point. For example, let me give you this beautiful example. Let's say I have a function like this way. I don't know what happened exactly at this point, but I know exactly what happened after that. It started to behave like this, right? And I don't know what happened to the x equal to a. So what I do, I come from left, I come from left hand side, and I study this point as close as possible. So the vicinity of this point is here, right? So I calculate. I do my experiment and calculate what happened to this vicinity, and I found what is called as left hand limit. Okay, let's say, and I represent that left hand limit as a minus. A minus means just left. Very close to a, but not a. You just left short in order to have equality with it. So yeah. And what we will do, and one more time we do the experiment, and we get as close as possible to this a point from the right hand side, and the vicinity turns out to be this, right? And we write this right hand limit is equal to f of a plus. I hope you understand the idea of a plus and a minus. What do you mean by a plus and a minus? So the a plus basically tells you just right hand side of the a, just right hand side, just right. Okay. And a minus basically tells you just left of the a. So what you understand? So what you do? So the understanding is that you first calculate what happened to the just left, and you understand what happened to the just right. If both the behavior is same, and what do I mean by same? If I say the behavior is same, is that means the left hand limit is equal to the right hand limit. Whether the behavior at the exact left, the behavior at the right is same, then I can say that the behavior at the center is also same. But in this case, but in this example, what we see this, the left hand limit is not equal to the right hand limit. The behavior at the just extreme left, just left, and the behavior at the just right is not same. The behaviors are different, right? That means I cannot claim what happened at x equal to a. So basically this tool of limits fails to explain what happened exactly at x equal to a, right? So when I can say this happened, when we have this kind of situation where the left hand limit and right hand limit are same. For example, I had this graph, there is a puncture over in this line, and that line continues to go, and this is my f of x, and this is, yeah, okay. And so and I just want to understand what happened at x equal to a. So what I do, I calculate the behavior exactly just left of the a point, and I calculate what happened and the behavior just right of that a point. In this case, the left hand limit is equal to the right hand limit. Okay. And what do I mean that? What do I mean by that? That f of a minus is same as f of a plus, right? Then I can say that f of a is equal to the f of a minus and f of a plus. So this is where you can say what happened at x equal to a. But in the case of earlier example over here you can say the behavior at the left and the behavior at the right is different. That's why I'm unable to say what happened at the center, what happened exactly at x equal to a. So the whole idea of limits and everything is that you're trying to understand the behavior at a point which you couldn't get because of some reason. Maybe you are unable to design experiments such that you couldn't understand what happened, but you want to understand, you want to get some estimate, right? because that has because that might be very valuable information. Maybe maybe you don't have a good experimental setup, right? Maybe you don't have good computer to work with. So, but also very much interested to understand what happened exactly at x equal to a. So the whole idea of this limits, the tool of the limits and calculus is that you understand the behavior around that, and if the behavior around that is same, and you say that the behavior at that exact point is also same and equal to that value. So over here you try to make a discussions points which are very close, right? And if I say, for example, like what do you mean by very close? Because that need to be understood. Let's say I cannot compare this point with this point, right? They are very far apart. They might have same behavior or different behavior, but those behaviors are not related, right? But why am I saying that these two behaviors are related? Because they are very close, extremely close. And we know that our original natural systems, the systems which we see in our real life, those are continuous, right? Those are continuous kind of thing, right? Each and every points are linked to each other. So over here we are trying to understand two points, the behavior of the 2 points which are very close, and they are somehow connected. Why they are connected? Because we want them to be continuous, smooth and everything. Yes, yes. So the question is, can we get limiting value at sharp? Yes, we can get the limiting value at the sharp points. Yes, we can get the limiting value at the sharp points. That's a very good example, the one which you have asked. So the question was, let's say if I have a function y equal to mod x, okay, and the graph of y equal to mod x looks like this, and you can see over here at x equal to 0 we have a sharp point, right? We have a very sharp point, it's a jagged point, right? And I just want to understand what is the value of f of 0. I just want to understand. So these limits will help me to understand this point, because you can understand this jagged point is very hard to get experimentally. We can understand in experiment you can get these lines very easily, but in experiment to get this point is very hard. It's not an easy job to experimentally or in a real life to understand this point. It's very hard. Maybe mathematically you can see very easily, but in experiment in real life it's very hard, because in nature we don't see sharp corners very often. We see smooth behaviors and everything usually. But since you have asked this question, so yes, we can understand, we can calculate this answer. And what we found that, let me give you how to do this calculation easily. So we can write this function as this way. This is equal to x and this is equal to minus x. X when we have x positive, minus x when you have x minus negative answers. When we give negative inputs, we have negative of that negative, like for example over here. So we see that this function have two branches. So what you will do, you first calculate what is left hand limit, which is basically f of 0 minus, okay, and the way we calculate this is by doing this. We calculate what happens is f equal to f of minus h. So 0 minus, let me first remind you that 0 minus can be written as minus h, and 0 plus can be written as plus h, such that h is very close to 0. Hopefully you understand this arrow thing, right? H, right arrow to 0, this particular thing means your h is very close to 0, very close. It's a positive thing, it's a very close to 0. So this is how you can understand the behavior over here and over here. So what I'll do, I'll just calculate that. So what I found that this is equal to the minus of minus h, which is plus h, and if I calculate what is this right hand limit, this turns out to be f of plus h, which is again plus h, and we see that left hand limit is equal to the right hand limit. Over here we see that left hand limit is equal to the right hand limit. That means behavior at the just left and the behavior at the just right. The behavior at the just left and the behavior at the just right is same. So what do we conclude? We conclude that so the behavior at exactly at the center, which is x equal to 0, is equal to both the behaviors. So we write that f of 0 is equal to the f of 0 minus f of 0 plus, which is equal to 0, because this h is the 0 itself, right? Because they are very close to 0. I hope I answered your question, right? First I need to, after this I just want to let you know when this tool fails to help you, when we cannot estimate. So the situation when we cannot estimate is that when we have a discontinuous graph. Let's say you have a graph here and it just just discontinuous in a fair amount of thing, right? In a fair amount of points. Let's say this. Then it's very hard to understand what happened here. It's very hard because now you don't have an isolated point, right? You have a fair big amount of values of x which you don't know, and it's very hard to understand because you might have various things, right? You might have gone this way or you might have gone this way. So there are lots of possibilities, right? So in this case it is very hard to understand what happened here. When you have a fair amount of range of x, you don't know what happened. But you can say what happened over here. What happened over here, but not in between. You can comment about the neighboring, you can comment about the boundaries, but you cannot comment about what happened in between, because now you have a good amount of x which you don't know, a set of x which you don't know. In the above case, you can say what is the answer. In this case, you can also say what is the answer over here, because that's an isolated point. It's a single point which you don't know. But in this case, you have a range of points which you don't know. So in between, there are lots of possibilities, almost infinite possibilities could happen. It's very hard. We have next level of estimation which we call as differentiability. In the future classes, you will learn this differentiability. So this is the next level of estimation, when you cannot estimate using limits. Limit fields. In this case, you cannot estimate what happens using limits. It's very hard. So the next level, you jump to the next level of tool, which is called as differentiability. So using this differentiability, you can somehow comment what happened. And how do we, so what is the idea of this differentiability over here? We just see what happens to the slopes. We see what happened to what was the slope earlier, what was the slope at the end, and we just try to match the slopes. And this is how we try to get, maybe the red line happened, maybe the green line happened, maybe that orange line happened. So in the future classes, we'll discuss this differentiability. So this limits, differentiability, integration, they are all techniques and tools to estimate certain values which you couldn't. I hope my message is clear, right? because I saw that this message was not delivered in the lectures which was given by the professor. I think the concept which I just said you is what relate to the real life example, because there are some students, they are from industry background. I hope they will like this answer more, and this is also a motivation to understand why we are interested in learning limits and differentiability, because there are various mathematical situations in which we want to estimate but we couldn't. So we try to develop tools and techniques. These are the tools, these are the techniques, and through this set of ideas we can get the idea what through this set of ideas we can get the hint what could have happened in between. For example, over here, I hope my message is clear, right? Any thumbs up, so that I can understand people are getting what I'm trying to say. Yes, you have a question, Abika? Abika, you have a question, you can unmute yourself and ask question. See, in this session I'm just trying to give you the idea like why we are learning limits, okay? I'm not interested in doing the questions so far currently. Right now my motivation is to make you understand why we are dealing with all these things. Okay, the question is, so is it possible that an exact x equal to a, the function may not have value, but in the limiting sense we can get a value? Yes, yes. Exactly at x equal to a, you might not have exact value, but what we do, we study the limiting cases. Limiting cases basically means we study the vicinity of that point, and if we find the values in the vicinity of that point is same, then we conclude that yeah, the value at exactly x equal to is also same. Because the idea in my head is that the line is continuous, right? I might not have the answer at this point. I might not have, like example that you asked the question you asked exactly. But what I do, I just understand the behavior at the vicinity, and if the behavior in the vicinity is same, then I say that in between the behavior is also same. And why am I able to say that? Because these 2 points are very close, the vicinities are very close. Try to understand, in calculus we are trying to these 2 points are how close these 2 points are, as close as possible you can think of, as close. These points are that close. So for example, the idea of infinity. So idea of infinity is very large, like as large as possible you can think of, even more larger than that. So over here the closeness, the idea of this closeness of these points are, they are so close that you can think of. Okay, so yeah, just by understanding the behavior in the vicinity, we claim what happened exactly at this point. We claim the behavior at this point. Yeah, yeah, exactly. So can you explain the concept x goes to infinity in the trigonometric one? Okay, so the idea of the x goes to infinity in the trigonometric function. First you need to understand the idea of this infinity. What do you mean by infinity? So whenever we have this idea called as infinity in mathematics, you first need to, the first picture which you need to get in your head is that it's something very large, very large. For example, you come up with a number in your head, let's say m. So the m is basically less than this infinity. The first thing you need to understand, what do you mean by infinity? It's a very large number. So whenever you see this x tends to infinity anywhere, not only logarithmic, in exponential, in any kind of function, whenever you see this, that means the value of that x is very large compared to everything, compared to every number which you see around there. So I can give you example. For example, tan inverse of x is tan inverse of x, and if you take x tends to infinity, this value comes out to be pi by 2. I hope everybody understand what you mean by inverse function, right? The reason I take the inverse function because I want this value to be some finite value. So over here the x tends to infinity means, let me draw the graph for you. So the tan inverse x is basically looks like this. Okay, so this is your tan inverse x, and this is your x, and this is your function. So you can see basically you can see this line, this arrow on the x-axis. Okay, so this infinity is basically over here, this arrow. So have you heard this something called as asymptotes? So infinity is basically an asymptote to this x-axis. I mean, the asymptote number to this. So okay, just forget what I was saying here. For now, just keep in head is that something very large number, and you put inside a very large number. Over here, you put a very large number. So the moment you put a very large number, this infinity gets mapped to this over here, which is pi by 2. I hope you get the idea, right? Can you answer like, have you got the idea? Okay, sir, in case of discontinuous graph, can you throw more light on estimating for x equal to a in real life scenarios? Okay, so I can give you my personal favorite example because I have worked in one of the experiments. So the idea of the experiment was to calculate frequency related to some parameter, let's say alpha, I don't know, some alpha, and we got graph like this, and the experimental setup was very hard, such that we don't know, we can't claim about this, we couldn't set up the experiment for these values of alpha, we couldn't, but for these values of alpha we could set up the experiment, but we don't know what happened here, we don't know, but we wanted to understand what happened here. So we had various possibilities. The graph could have gone this way, maybe the graph could have gone this way, maybe the graph could have gone this way. Let me take, there were three possibilities, right? But we chose the middle one, the blue color. But we chose the blue color for our result. Why we chose the blue color? Is because of the differentiability in this case, not because of limits. Limits at best will tell you what is the value over here at this boundary, but limits fails to explain what happens in between. So in between we need something, a bigger tool, which we call as a differentiability. See over here I have took the case of discontinuity, where I have as a question which was discontinuous graph. Sorry. We need to understand there are various types of discontinuity we have, various types of discontinuous graph we have. You might have isolated point, you might have isolated points, or you might have a range of x is missing. For example, range of alpha in this case, a range of alpha is missing. So the case which I am discussing now, in which you don't have a range of alpha in between. There is another case where you have a very isolated points like this. You have a point here, then you have point here. Oh sorry, this. Let's say don't have point here, point here, point here. You can see these are isolated, right? This graph is also discontinuous, but the discontinuity is in the isolation, right? So you can solve the problem, you can get the estimation at these points using just limits. These are enough. Why? Because now you need to understand the behavior at this point. You study behavior at this point, and in this case limit successfully explains what happened over here. In this case you have to study here, and limits will successfully explain you what happened here. So this kind of discontinuity is not that very difficult to deal with, right? Because the discontinuity is in with because of the isolation, because of the isolated points. But in this case you don't have the whole range, and in this case limits fails to explain. At best limits can do is to explain you what happened here at the boundary, but it fails to explain what happened in between. So we need a bigger tool, a bigger class of tool, which we call as a differential gradient. So what we do, in my case, what we did, we selected this between this middle line, this blue line. Why? Because just left of this range we have a flat line, and just right we have the flat line kind of trend, right? So we expected in between also we might have a flat line. And since we see that in real life, in real scenarios, real life scenarios, we don't have abrupt changes, right? We have gradual changes, and the blue line, the blue line shows some gradual changes. Okay, and green line, orange line shows something unusual behavior. You don't expect. Okay, I hope I've answered your question. Can you give me a thumbs up? Okay, thank you. So what if the tan inverse x is divided by x, where limit is in? See, this is Puneet, the question which you asked is a algebraic question. For example, you have this tan inverse x over x. This question you have asked. So this limit will go to 0 as x tends to infinity. Why am I saying that? There's a good reason. The reason is that if you see the numerator, if you see this numerator, the numerator goes as pi by 2, but the denominator goes to some very large number. Very large. So something which is finite, which is a small number. See the compared to the infinity, pi by 2 is a small number, right? So you can understand the ratio will be very close to 0, right? I hope this answers your question, right? I just solved the problem just by understanding, okay? Understanding the behavior of the function. You can see from here, for example, this is a pi by 2 thing, and this is how tan x moves, tan inverse x moves, right? So you can say the numerator at best, what value can go numerator at best? Pi by 2, that's it, right? But in the denominator, what value it can take? Infinite, very large number, right? So something which is finite number divided by something which is very large, infinity, is definitely 0, right? Let me tell you important thing after this. Oh, I have more questions. Do limit exist at the point of discontinuity? Limits do exist, but not in between. Limits do exist over here, which we call as left hand limit thing. Let me use different color. Yeah, over here, but not in between. In between limits don't exist. We need to have a different tools of ideas to understand what happens in between. Limits fails. Limits at best will tell you what happened at the boundary. Okay. Limits will help you to understand these points. This kind of discontinuity you can understand with limits, where the discontinuity is because of the isolated points, not because of the whole range is missing, right? I hope this answers your question. Okay, yeah, Pritam. Okay, I got your answer. One more important thing I just need to clear, because this is very important. Let's say you have some finite number, okay, and if you multiply this with 0, you will get 0, okay. And let's say you have 0, if you multiply with another 0, you will get 0. We have no disagreement on this. But if we have infinity, some infinity means some large, very large number, but I don't know, some very large number, if we multiply with this 0, what do I expect? Any answer? What do you think? What do you expect? Some negative, positive, finite, 0, what? Infinite? What do you see? 0? Think carefully. Think carefully. Yeah, exactly. That's kind of undefined thing. Yeah, that's undefined, because the possibility which it can take, it can be 0, it can be finite, it can be infinite as well. We have to see the structure of this infinity and 0 here. The moment we know what is the structure of this infinity and 0, we can claim to which answer this will fall. But keep in mind, this can be 0. Yes, this can be 0. This can be finite. See, 0 and finite are same thing, so I will remove this thing, okay. It can be either finite or infinite. So based on the structure, we can claim whether this will fall into a finite or infinite. So you have to see this, you have to check this. Can I give you an example of this? Yeah, I can give you one example. For example, 1 over x, okay, and let's say into sine of x, okay. And I just want to understand what happens at x equal to 0. I just want to understand the behavior of this function. I can draw the graph of the function. It looks like, yeah, it looks like this. Since I have drawn the graph, you know the answer exists, right? Just by looking into the thing, you can say. So this is the graph of sin x by x, and you can see at x equal to 0, it has a finite value which is equal to 1. So the answer is 1. But over here in this case, if you see this 1 over x, if you see carefully this 1 over x, this goes to infinity, right? So very large number. But if you see this very carefully, this is 0. I can draw the graphs, this and this. This is for the 1 over x, and this is for this sin x. You can see for the sin x, x equal to 0 is 0. But for the 1 over x, it is some large value, right? Some large value here. Let me use another color if you are unable to see carefully. So you can see it's a very large value. So this is a typical example where you have infinity into 0, which gives a finite number which is 1. Neither 0 nor infinite, it's 1. I can construct many examples. For example, I can multiply this with 5. So what do I expect? I do expect here 5. So I might end up different answer altogether. So this can be infinite, finite. So what we call this kind of forms of math. So we call this kind of mathematical forms as indeterminate form. They are actually undefined unless and until I know the structure. So we have this indeterminate form like infinity into 0. It can be anything. You have to see the structure and calculate and understand. We have this kind of a structure, this interesting structure, my own personal favorite. We use this a lot in physical scenarios. Infinity minus infinity. You know the difference of a two large quantity. So don't see this 0. It can be plus infinity, it can be minus infinity, it can be 0. Yes. Since there are many answers, isn't it indeterminate? Yes. Actually, these are indeterminate and undefined in the sense we don't know the structure. We need more definitions. Undefined in the sense that they are not well defined. So I hope you understand this one. Hello, Harini, do you got the idea, right? Why do I? Yeah, thank you. So here the undefined means we don't know the structures well. I need to know the structure so that I can comment. But more accurately, they are called indeterminate. Yeah, we cannot determine them. It can be anything. We need to see the structure. We also have another example, that is 0 over 0. It can be anything, plus, minus, anything. Again, we have this situation in infinity over infinity. You can't say. We have another situation, 1 to the power infinity. It can be anything. It can be 1 or it can go to infinity. So this is also in indeterminate form. Can anyone give me another example of indeterminate form? Are there any other indeterminate form? Maybe in the next, maybe in the coming sessions we'll discuss this. But I hope we got the idea that there are these situations. We need to be very careful, super careful. Indeterminates are the biggest surprises one can see, and in real life, uh, this indeterminate plays a very important role, very important role. When you do physics, for instance, there are many situations you see we shouldn't expect that answer, but it comes. For example, this theory of relativity and things, right? And that theory of relativity, you have seen this, nothing can travel faster than the speed of light, right? In order to justify this theory, indeterminate plays a super important role in that. Super important role. Using this indeterminate, we also prove that photons, basically the light, they don't have rest mass. We claim so many important physical uh, understanding, physical understanding of the nature and various things using this indeterminate form. And over there, this limits, continuity, differentiability plays an important role. I hope everybody understand the idea why we are learning this. So this was the concept. Does anyone have any question? Please feel free to ask. Like, I'm here just to help you guys, because the lectures given by the professors, they are available everywhere. You can go anytime and hear them. I'm here to answer all the questions which you have in your head. I'm here trying to understand, like, you guys are getting subject or not. Any question, anyone? What is the definition of vicinity? Vicinity means neighborhood. Yeah, that's a very good question. Vicinity. Vicinity means neighborhood. For example, let me explain this using this idea of, have you heard this epsilon delta notations in the lectures? In the lecture 5, I guess. In the lecture 5, professors use this notation of this small epsilon, small delta to define what is called as neighborhood, vicinity and all. I'll help you to understand this. So, vicinity, let me give you a simple example. Let's say I have a rectangle and there is a point somewhere here. There is a point. I can't understand this point because somehow I'm unable to do experiment to this point. I cannot create this point. It's very hard. But I can have these points in my experiment. Those points which are very close to that, very close, and we call that as a vicinity. So vicinity is that literal dictionary meaning, the neighborhood. Vicinity is very close to that point. The points which are very close to this orange thing, right? So those are basically those red one, right? So we call those red one is the vicinity. So what is the definition of vicinity and how close is this? Helps to understand the definition of discontinuous graph. Yes. Okay. So when do I say when the function is the graph is discontinuous? When your when your behavior at when the behavior in the vicinity is not same. Let me give you example by this one. Okay, this is a very good question you have asked. This is a very fundamental question, and we ask this question everyday basis. When you go for the higher education, you ask this question in everyday basis. Let's say the vicinity to this black point, this kind of vicinity over here. Okay, and I'm marking this as a orange to tell you that this is a different set of properties. Okay, and I also have vicinity over here. See, all these are vicinity points, but I'm giving these different colors because to make you understand the behaviors are different. And let's say over here, so all these three colors around this black dot, all these three colors are vicinity to this black point, but I'll say that this structure is discontinuous, not continuous. Why? Because all of the three have a different properties. If they were continuous, they must have same property, but they are discontinuous, they don't have same property. I hope you got the idea how do we say the things are discontinuous in the language of vicinity, right? If the behavior in the vicinity of that is not same throughout this vicinity, then we cannot claim what happened here. Then we cannot say what happened to this black dot. Now I cannot say anything since the behavior of the vicinity is not same. If there is some homogeneous behavior around that black dot, then I could claim something about this black dot, the behavior at that point. Oh, okay, so you got the answer. Thank you. Yes, Devika, you can ask. You can unmute yourself. So you need to understand mathematics is a set of ideas, not just algebra, right? So yeah, you need to understand. The real mathematics is to understand what's happening. Yes, any other questions? The question which you asked, definition of vicinity and how it is related to the discontinuity, is a very important question. This is the most fundamental question you have asked. So this is the answer for your question. And the next point I need to tell you that we use this epsilon delta notation. Let me first tell you what do you mean by this notation. So we have this usual English letters, this A, B, C, D, this capital letters, right? And we have the small letters A, B, C, D. So we also have something called as Greek letters as compared to the English letters, where we have this something called as alpha, beta, delta, gamma, nu, this kind of things. So these are the small letters, Greek small letters. And what are the capital letters, what you see? So the capital letters in the Greek, you have this capital Pi, capital sigma. Small sigma is this. This is small sigma and this is capital sigma. This is small pi and this is capital Pi. And the notation in mathematics we have is that whenever we have small letters, the picture in my head is that they are very small quantities. Very small. For example, in the definition which you saw in lectures is that epsilon delta. So whenever you see this epsilon and delta, these small numbers, the immediately picture in your head should be they are very small numbers, very small. They are very close to zero, very small. And we use this to mathematically write what do we mean by vicinity, neighborhood, right? Over here, I said everything, by through English, right? Through English, through pictures. But how do I write this mathematically? So I need these notations, and this notation plays an important role. So whenever you see these Greek letters, which are in the small case, small Greek letters, the picture in your head should be they are small quantities. Okay. So whenever we want to mathematically write down a number which is large number, we use capital numbers. For example, capital M. For example, capital M. We will see this a lot in upcoming videos. So I hope this idea is clear to all. And let me write down how can we write this everything. How can we write all of these things which we discussed in a mathematical fashion? So we say that, let's say we have this function and we want to understand this behavior of the function at the point A. So hopefully you understand the idea of this arrows, right? So this arrows basically tells you, very close, vicinity, those limits ideas, this concept of ideas, limiting values, I mean to say. So I just want to understand what is the limiting value of the function when the input is very close to A. And let's say the answer is L, some L, some L. So another way to write down this, see, these are just notations and these are some representations, nothing serious. Okay. So this is also another representation which you might have seen a lot in your 11th and 12th standard, maybe in higher schools. Okay. But this is somehow a new notation. Usually people use this a lot. I personally use this about notation a lot. But these are notations. Don't take it very literal. Okay. These are just notations, and the people write this mathematically as the difference in the value This is the mathematical way of writing, a more proper mathematical way of writing. This is in terms of neighborhood, vicinity, and I'll tell you how do we use this epsilon delta to define vicinity and all. We have this. Oh, I think I made a mistake here. Yeah. I'm basically trying to simplify as possible. And x minus a. Yeah. So let me make you understand what is this notation is. So first you need to understand what do you mean by this. This is a modulus function. The role of this modulus function is to basically calculate the distance between the two number. Let's say in between these two vertical line, if I put x, so what does this tells you? This basically tells you what is the distance of this point compared to the origin. Okay, compared to the origin, what is the distance? So whenever you want to invoke the definitions of distances in your mathematical framework, you use this vertical lines to tell you, yeah, these are the distance and these are the stuff. So the idea is that this particular above line tells you the distance between the actual answer and the limiting answer. They are very small. And how do I say that they are very small? We use this epsilon to say that the distance between the actual answer and the limiting answer is very small, because my epsilon is very close to 0, my delta is also very close to 0. So basically what I am doing that, let's say I have this might be a little confusing, but hang on, you will understand what is happening here. Trust me, just hang on. Okay, so let's say this is your actual x equal to a, and this will be your x equal to a plus delta. This will be x equal to a minus delta. So the thing which I have wrote in the x-axis is basically what this tells you. Okay. I mean, hopefully do you understand this idea, right? And so basically what I have created a small interval around the point which I am interested to study. I'm interested to study in this point, right? But I don't know what is the value at that point. If I have known, then why do I need this limit idea? So what I do, I create a neighborhood here. You can see I have created a neighborhood here. can see I've created a neighborhood, right, by using this delta thing, right, and this is how I write down mathematically. I hope everybody can see now, and this is how I create this neighborhood here mathematically. Okay, so the idea is that, let's say this is your function sum, and I want to understand and let's say this is my actual answer. This is my actual answer. So what I do, since I don't know my actual answer because I cannot do the experiment and understand because of certain limitations. Yeah. So I also create an interval around here. So this is actually f of a plus epsilon, f of a minus epsilon. Hence I have created an interval here. So I have created interval in both x-axis and y-axis. Around what? The values which I am interested. Hopefully everybody can get, right? Hopefully all are getting the idea. Can you give thumbs up, anyone? If you are not getting, yeah, okay. So I have created an interval on the x-axis and also created interval on the y-axis. Around what? To which I am interested. So this is my goal, right? I am interested to understand this. But since I cannot get because of my certain problems in experiments, but what I can study is this. I can study this. So the above mathematical definition which we have wrote here, it tells you that if you pick any point in this interval, and you feed this in this function, you pick any point in this interval, you feed this in this function, this will always end up inside this interval, always. Every point in this interval will end up inside this interval, and you can make this interval as small as possible you like, if limits exist. That's very important. If limits exist, then you can narrow this intervals as short as possible you want, and you will keep getting answers, such that these points will fall, or you can say map these points. These points will get mapped to these points via this function. I hope the idea is clear, right? So since the concept of limits is for experiments that can't be conducted at x equal to a, what if the possibility of knowing f of a to verify the correctness of the limit, isn't its assumption still? See, the idea is that the whole idea of this experiment and all is basically one of the real life example I have given. Real life example. Yes, I can understand. In order to give validation to what we have found, we have to wait until we get another best technology, right? Since we don't have that good technology, so for now currently we can get estimation. And have we measured this correctly? The future technology will tell us. Okay, hopefully you can understand. For example, through physics, through mathematics, we can estimate infrared radiation exists. You can estimate infrared radiation exists, but you cannot detect those infrared radiation from your eyes, right? Because eyes is also an instrument, right? And that cannot detect those infrared radiations. So you waited till I developed a technology which detects those infrared radiation. So we have to wait until we get a good experiment set up. Hopefully that answers your question. So this experiment thing is basically an idea, an abstract idea to make you understand. See, we use this limits continuity in a daily life problem. It's not just that we just study for granted. We really use this a lot. We have many situations. For example, if you see the stock market thing, they are highly unpredictable. Most of the theoretical models don't fit in. It's very hard to detect what happens in this particular frame of time. So there are many analysis, what we call market analysis. Those analysts, they basically use these ideas of this calculus. They use this calculus to estimate when to buy, when to sell, when to have this, add this stop loss, when to profit book, want to do. So they do some predictions so that they make a good choice. So all these things makes you to have a good choice. It helps you. There are many situations in real life, those are probabilistic, they are not deterministic. Hopefully you do, hopefully you all guys understand what you mean by deterministic and probabilistic. So in probabilistic you don't have any control, everything is probabilistic outcome, but you want to make some decision. So using this you can make a decision, you can have a good decision. Okay, so the question is 0 by 1 equal to 0? Yes, it is 0. 0 by 1 is exactly equal to 0. There is no ambiguity in that. If would have asked me like 1 over 0 is what, that's undefined, that's clearly undefined. But 0 over 1 is 0. So, yeah, since you have asked this question, let me make things clear. Undefined thing is a very different thing, indeterminate is a very different thing. We call things undefined because it's just end of the discussion, that's it. We cannot say any single word further. It's just undefined, we just reject it, we don't accept that. Indeterminate thing, you cannot determine what is the answer, but there is some answer, there is certain discussion you can have on. But in undefined you cannot have further discussion, it's just end of discussion. Hopefully this. Hello, hello everybody, can you hear me? Any other questions? The whole idea of Leavitt's calculus, everything was actually first invented by a mathematician. There were two mathematicians like Leibniz and Newton. They both independently worked out, and the interest for them is to understand the behavior of heavenly objects. Heavenly objects, I mean to say, uh, like moon, planets, those objects. They want to understand what are the behavior of those. They just want to understand the trajectories. Then again, understand, if I tell you something that I want to know the trajectory of a particle, any motion, any evolution, any kind of trajectory word, whenever you hear something called as trajectory, the first thing that should come into your mind is that calculus, because calculus is a tool which tells you how can you plot a trajectory, how can you get a trajectory. So basically, calculus records the changes the system have. Okay, and so I hope you all guys got the idea of this interval thing. So, the next discussion which I want to have is something called as um, differentiation. Yeah, something called as differentiation. It's a very good topic to start. Since professor have cleared a little bit, I take a mistake here. Again, we are not talking algebra of differentiation, we are talking the meaning of differentiation. So the meaning of the differentiation is to basically tell you what is the instantaneous rate of change. And what do you mean by instantaneous word? The literal English meaning of instantaneous is that what is the rate of change exactly at that instant. So let's say you might have a variation like this, a cool variation for example, and you can see this is not a straight line. And why is it not a straight line? Can anyone tell me why we call a straight line a straight line? Why is it so special? We call it a straight line, but we are not calling this as a straight line. We call this the curved line. Curved line is a different thing, straight line is a different thing. And what is the main key property which differentiate them, which separates them? Can anyone write down a key word? The key word, what is something special about the straight line which curved lines don't have? Can anyone write down? Any comment? Any answer? The curved lines are also predictable. We can predict them. Straight lines are also predictable. Predictions are not the answer. They are something more special than prediction. The direction of movement don't. Yes, the answer is yes. You are very close to the answer. The answer is slope. The direction of movement don't change with respect to time. But this I won't consider this as a good example. I'll consider slope. We consider straight line as a straight line because the slope at each and every point is same. But in curve line, the slopes are different. And what differentiation captures? Differentiation captures the slope at a given instant, at a given point. For example, it captures the slope at this point, it captures the slope at this point, it captures slopes at every point, and you do predictions based on this slopes. For example, this case, my favorite or my personal case, uh, we predicted that this is the answer, not the green one or the other one. Why? Because of the slope. Through slopes we predicted what will be the direction, what will be the orientation, how things will evolve. Because we saw that the slopes were like kind of a flat thing here, right? Before and after. So I expected the slopes here should be also similar, not same but similar. So this is the importance of slope. This tells you the prediction. This actually predicts. Limits will estimate what is the value, but if you want to predict how things are going to go, keeping the fact that assuming the trend remains same. The trend. What do I mean by trend? See, these vicinity points, they will follow same trend, right? But these two vicinity points, they don't follow the same trend. They are completely far apart. They might have same or different, but I don't care because they are not very close. But when we have points which are very close, they have same trend. And the moment I know the slopes around here, I can predict. If I know this point, I can predict this point. If I know this, I can predict because of the slope. And that's why the differentiability becomes very important. It helps you to predict. For example, if I know the trajectory from here to here, from experiments, I calculated the trajectory from here to here. Now suddenly my machine stops working, and I want to understand what is the further trend. So how can you do that? So you need to first assume something about your system, that your system is not changing abruptly. Okay, there are not something crazy things happening there. We are assuming the trend remains same. The similar kind of trend is what happening. So under this assumption, you can create this whole curve. How? Let me tell you. For example, when you were tracing out this trajectory, every time what you were doing, that what you were doing, you were basically calculating the slopes each and every time you were doing the measurement. You were recording the slopes, and since you know this point and you also know what is the slope at this point, you can somehow estimate this point as well. Let me use another color. Yeah, you can estimate this point, maybe blue. You can estimate this point just because you know the information about this point and the slope at this point. You can get this point, blue point. This is what tells. Let me tell you how and why am I saying that. This might be a different angle which you see the problem, right? So my goal is to basically motivate you. There is a question, right? So the question is, sir, is that y function is not differentiable at sharp edges because in the vicinity of sharpness slopes changes? Yes, exactly. So the argument which you gave for the sharp points is exactly true. So this is why we say whenever we have the jagged points, sharp points in the graph, we say the function is not differentiable at that point because around the vicinity the slopes are not same. If you see this over here, right? You can see over here the slope. Let me use another color. Yes, the slope over here is +1, but over here the slope is actually -1. So just left you have a different slope, just right you have a different slope. That means you cannot comment. That means you cannot comment about the slope at this point. And that's why we say this graph don't have any slope. I mean, not don't have any slope, undefined slope at x equal to 0. That's why we say this function is not differentiable at center at x equal to 0. They're not differentiable. So you can understand the whole idea of limits carry forward to differentiability. There is no difference, right? In the case of limits, you are talking about the value of the function, but in case of differentiability, what you are talking? You are talking about the rate of change, right? In the case of limits, you are talking about the value of the function, but in the case of differentiation, you are talking about the rate of change. So if the rate of change to the left is different, to the rate of change to the right is different, then you cannot comment about the rate of change at that exact point. That's the whole idea. So thank you for raising that excellent question. This was an excellent question, I would say, because this example illustrates the point which I wanted to tell you. Let me tell you why I'm able to estimate that blue point over here. So the change in f, the change in f or change in x, this is what we call rate, right? That's what the definition is. Let me write this as some y thing. No, let's keep it f only, since everything is in terms of f. So we can write this f. Let's say I'm talking about this x equal to some x equal to a point. Let's say I know this x equal to a point. So we can write this x equal to x plus a this would be fine. A plus h minus f of a over h. Now let me tell you what is this h is. So this h is basically, see, we have these two lines, right? So the gap between them is h, right? So what I saw, the value at the blue minus the value at the green divided by h. This is what the rate, right, at x equal to a, right? That's what the rate of change at x equal to a. So you can see that the moment I know what is my rate, the moment I know what is this, I can estimate this, right? Let me write down. So this can be written as h times of rate plus f of a. This is the important thing which I want to emphasize. Let me color this, if you feel. See, this is what the blue point is telling you. This is the value of the function of that blue thing, you can see there. And this is what your green thing. So if you know the value at the green point, if you know the value at the green point and you know the slope, if you know these two things, we can easily estimate, right? We can easily estimate the blue point. So that's why the knowledge of rate is important at every instant of time. At every instant, because using that rate and the value at that particular point, you can estimate what happens next, what happened next. So you can keep on doing that. You can keep doing that iteratively, and you will construct this. You'll construct this whole trajectory, right? construct this whole trajectory, keep constructing this trajectory, even without doing the experiment, right? But in doing this, you need to make sure that my system is not doing any crazy things, right? Any crazy things, any stupid things. It's just doing some smooth things, right? But the problem is that you need to know the prior knowledge of rates in order to do that, right? And because what I'm saying that you need to know the rate at each and every point, and just because of the knowledge of rate and the initial point, and this is my initial point, right? If you know this initial point and if you know this rate, you can basically create a whole trajectory without doing the experiment. I hope what I'm saying is clear to all, right? But you can understand doing this very hard, right? Because I don't know the rate every time, because in doing this I need to know what is the rate at each and every instant. I don't know. That's why we are unable to do this. That's why we have to do experiment in each and every point, because I don't know the knowledge of rate at each and every point. Okay, but the whole idea which I've illustrated here is to make you realize the importance of differentiability. So this is how you create, this is how you write down physics, this is how you write down the evolution, this is what we mean to write down things. Okay, so the question is, the vicinity around sharp points and the vicinity in discontinuous graph is both non-homogeneous. First I need to understand okay. So first I need to understand, you're talking in terms of what, differentiability, or in the terms of limits? First let me know that. Oh, in the terms of limit. Say in the terms of limit, if we have jagged points, let's say we have a sharp points, limits don't care. Limits don't care those sharp point and jagged points. As long as you have a graph, you plot the graph without lifting your pen. Limits don't care. The limits do care whether this line is continuous or not. This line is drawn using a single stroke. You have not lifted the pen. Limits don't care about the sharp points. Limits care what is the value just left, just right. Limit care about the vicinity, the values at the vicinity. But when we talk differentiability, so differentiability, the language is same. The only difference is that instead of talking in the terms of values, you talk in the terms of rate, changes, slopes, in the terms of slopes. So the slopes is different around the vicinity. Differentiability has a problem in that. Okay, thanks. Anyone have any further questions? Since we left with 15, we have 15 minutes. I'm open to all the questions. If you have any request, we can fulfill that. Maybe in the next session we can clear up. Any questions? Anyone? I hope the instruction was clear. So my whole idea was to give you the motivation for this course. Any questions? So we will get the class notes. My class notes or professors lecture notes are already available in the portal. The things which we have discussed now, are you talking about that? I can provide you the things which I have wrote now. No issue in there. Okay, I'll provide you. I will provide you. No, don't worry. There will be, you will receive a link, a Google Drive link, in which you will find all the materials related to my context. Okay, is this fine? Okay, feedback. Thanks for giving a more meaningful and non-theoretical meaning of the basic concepts. Yeah, thank you, much appreciated. What didn't you hear clearly? Oh, so I said that you will receive a link, a Google Drive link, in which there will be each and every material related to my context. Like whatever things I'll cover, whatever my materials are, you can find those materials in that Google Drive link. You will receive that. In future you will receive that. Okay? Just hang on. You will receive. You will also receive the today's what we have discussed in this note. So there are one more thing I also want to make you understand. Uh, let's discuss. Let's we have a time, so we can discuss what do we mean by integration. So can someone tell me what do you mean by integration? We have did this a lot. We see this elongated S kind of symbols, right? We see these things everywhere. What is this? What do you mean by this? Okay, mathematically I can see. Okay, this looks nice. But what this is trying to tell you? Because until and unless you understand what it means, it doesn't matter what you do. Adding small pieces to make a big picture. Yes, you are very close. Yes. This is what essentially this integration is. Yes, you might have heard this line, small milate jao, large banate jao. You know, keep adding the small parts to make a big picture. Yes. So one of the quick example is that everybody knows. It helps you to calculate area, length, for example, length, volume, higher dimensional volumes, all sorts of crazy things. Okay, so I just want to make things clear before closing this session. When to use integration, when to use differentiation. Can anyone explain when to use integration, when to use differentiation? I just give you the meaning of. We know the meaning of integration. We know the meaning of differentiation. Integration is what you keep adding the small things and get a big picture. In differentiation, you break down the big picture into small pieces. Now you can understand, right? When to use. Let me give you one small scenario. Let's say, this is a good example. This is nice. Let's say you have a graph, okay, and this graph looks like this, okay? And let's say this is the quantity A versus B. I want to calculate C, which is A into B. So how will you calculate this? How will you calculate this? Using differentiation you will calculate, using integration you will calculate. What you will do? How will begin? Yes, using integration. Yes, using integration. Yes. And why we can use integration over here? Why? So reason is that. So the idea is that, see, this A cross B is basically tells you what? Tells you an interesting thing which is called as area, right? This tells you an area. Why? Because in y-axis you have A, on x-axis you have B, okay? And whenever you calculate area, you basically what you do? You calculate this, right? And this thing can be calculated easily by adding these small rectangles. Right? By adding the small rectangles in order to get the full complete area. So what we do, we go to this special point. I don't know what is the special point. Let's say we call this x equal to x, some x, and this graph is from x equal to 0 to x equal to 8. Some x equal to let me write it as small l. Yeah, small l. And let's say this is some, something. So the idea is that, let's say this is a function, some y equal to f of x. So what I do, I go to this particular location, just x equal to x, and I construct a rectangle, and I will calculate the area of this rectangle, because my idea is that I'll keep on adding these small areas everywhere. I'll keep on adding the small areas starting from x equal to 0 to x equal to L. I keep on adding these areas. Eventually I will end up this area under the curve, area traced by under the curve. Yes, integration multiplication is repetitive addition. So here I am basically trying to give you the idea, like short idea what we are trying to do. So you can see over here the width of this rectangle is x, and the length of this rectangle is f of x. So what is this my small area? What is the area of this rectangular piece? Area of this rectangular piece is basically f of x into some h, you can say. We'll consider this width as h. So I made a mistake here, sorry for that. Okay, the width is h. I've taken a small width of h, and what I'll do, I will just sum up the whole rectangular pieces in order to get the whole area, complete area. So let me write down this way. So the complete area will be the summation of summation of all these rectangular pieces, and eventually we will end up with this symbol. And in the future session we will discuss how we got this symbol from here to here. Okay. I'll ask you another scenario. In this case, what we need to calculate? Let's say we have let's say we are studying a physical particle. We are trying to understand a physical particle where we have a graph for time versus position. Okay. And let's say we have some plot like this, some function, I don't know, sorry, there is a t here. Oh, I made a mistake. This is x of t. Let's say we have a graph, and you know what this graph tells you? This graph tells you the location of that particle each and every time. And my idea is to calculate what is the speed. What is the speed at time t0? What do you think? What we should do? How do we get this? How do we understand? We should, yes, it's a derivative. Exactly, this is a derivative thing. We'll do the differentiation because, yes, we'll do the differentiation because the speed is basically what? The rate of change of position with respect to time, right? So speed is basically measures what? The distance you've covered in the given interval of time. So this is the whole idea. I hope I have fairly motivated you for this course. Any question before we close this session? I'm open for the questions. If someone wants to introduce, they can happily introduce. If someone wants to know who am I speaking, I can introduce myself again. Yes? Question? Yes? Yes, Himel? Yes, you have a question, right? You can switch on your mic and say. So, would like to know more about you and your work. Oh, my work. See, I'm from a physics background. I do research related to quantum computing. Let me also write it down here. do research in quantum computing. I am currently affiliated to IIT Madras from physics department. My job is to do quantum error corrections. So what this quantum error correction tells you. So whenever you have some computer, right, it does some computation, it does some calculations. But the quantum computer is so sensitive to the environment, so sensitive to the noises. Like even a small photon, even a small disturbance can create a whole lot of problem in your computations, in your calculations. It can corrupt your data, it can corrupt your calculations very easily. It is very sensitive to your noises, very sensitive to your nature. It's very hard to maintain the physical scenario which this quantum computer needs. So my job is to basically reduce these errors because of the noises, to prevent those noises. Let's say the noise happened, how to correct that? So basically I work areas related to noise corrections, error corrections, noise prevention, noise protection, and how can we improve the efficiency of this quantum computer? How can we scale up this quantum computer? Because currently we have definitely we have a quantum computer, no doubt. We have quantum computers, for example, 400 qubits, which is a superconducting quantum computer. But the things which we want to do, which we wanted to do, the exciting things, the exciting problems which we wanted to do, the problems which our classical computer cannot solve. For that we need thousands of qubits to do that. Currently we are limited to 400 qubits around. So the moment we have a large scale quantum computer which is around thousands of qubits, so we can basically destroy the whole security systems currently we have within few minutes, within few time. Currently, for example, our banking system is safe. Why is it safe? Because the time you require to crack this particular security, to breach this security, you need more than hundreds of years, and nobody lives more than hundreds of years. So that's why we say our security system is safe. But the current security system can easily be broken down, can easily be cracked down using quantum computers. We have something called a Shor's algorithm. We have a quantum solution. We have a quantum solution. We have a proper algorithm. We have a proper understanding how to break down this problem, this security problem. We know how to crack down the security. But in order to implement that algorithm, we need a large amount of qubits to do that. We cannot do that algorithm just using 400 qubits. We want something thousands of qubits to implement that Shor's algorithm, so that we get actual quantum supremacy, which I currently believe to be. I hope what I said is clear, right? I do more quantum mechanics, quantum physics. I do more that stuff. Mathematics is my hobby kind of thing. Anyways, I like quantum physics. Quantum things are here to great sound and complex but interesting. You can feel free to ask me any question you feel. Here's my mail. Let me give you my mail. You can mail me if you find any problem. More specifically, I work in adiabatic quantum computing. So there are lots of versions of quantum computers like superconductor, D-wave, adiabatic, topological, gate-based. So there are thousands of versions, but I specifically work on this adiabatic. Adiabatic. Yeah, this one. Yes, I will teach on every Monday. Yes, that's true. Every Monday for the upcoming 8 weeks. I had decent questions, but I thought before discussing those questions, let me make you motivated, feel you motivated. Why doing these questions? the first, as a professor also said, if you are not understanding the subject, that's not a point. That's not a good thing. I hope now we will close this session. So thank you everybody. Hopefully this session was helpful to all. Next time I'll come up with more exciting things. I have many things to discuss. For now, just keeping myself reluctant to speak all those things. Eventually, when the discussion carry on, we'll discuss. Thank you, Hima. Thank you, everyone.